This problem states a 22-inch by 34-inch speed limit sign is supported on a 3-inch wide, 5-foot long pole. Estimate the bending moment in the pole at ground level when a 30 miles per hour wind blows against the sign. Okay, so we're given information about both the pole and the wind in this, and I'm going to just draw the sign out here so we remember. We have a visual for the dimensions. So here's my pole, which is 3 inches wide, and this is 5 feet. And then we've got the sign up here, which is 34 inches and 22 inches. And if we look at this from the side, we have our pole and our sign, and we've got wind blowing, and there's going to be a bending moment here that's going to be generated at the base of the sign. So the drag force that the sign's going to experience, we're going to have some drag force that we need to account for on the pole, and we're going to need to have some drag force we account for on the sign. For the purpose of calculating the moment here at the base, we are going to assume that these two sort of resultant forces act at the center of the sign and at the center of the pole. And so as far as dimensions go, this guy is halfway up, so we've got this at 2.5 feet. This guy is at 17 inches up the sign plus the 5 feet, so we're at 5 plus 17 divided by 12 feet. And so now if we write out our sum of moments equation, we have our bending moment equals 2.5 feet times the force of drag on the pole plus 5 plus 17 over 12 feet times the bending moment on the sign. So let's write out our drag equation. Our force of drag, let's do the sign first. On the sign is equal to CD 1/2 rho v squared A. So we have to find our CD for the sign. And for that, we're going to go to table 11-1 in our book. Let me bring up the the picture here. So this is what we see in our book. I'm going to put that over here. And the force of drag here, here's our velocity of the wind that's going against here. L is very thin, D is long, so corresponding to a thin plate, which is what this is, we see that our CD is 1.9. And so now we plug everything else into here, and we see this is 1.9 times 1/2. Rho here, we're in English units, so we need the density of air, which is, I looked this up, 0.00238 slugs per foot cubed, times the velocity squared. I've already converted the miles per hour into feet per second. (30 mph equals 44 feet per second. And then we're multiplying that by A, which is the frontal area of the sign. So it's 22 inches times 34 inches. And then that's going to give me inches squared, but I want it in feet squared, so I'm going to divide by 144 inches squared per foot squared. And then that gives me this all in feet squared. And you can convince yourself that the units here are going to work out to be pounds force. Basically here I have dimensionless, dimensionless. Here I have slugs per foot cubed times foot squared per second squared times foot squared. And so this foot cubes cancels with those guys, and I have slugs feet per second squared, and that's exactly what equals 1 pound force. So I can calculate this all out, and I get 22.7 pounds force. And then I just need to do it for the pole as well. FDP equals CD 1/2 rho V squared A. I need my drag coefficient for the pole. So I'm going to bring that in here just a second. Here it is. Same table, my velocity hitting my square rod with sharp corners, I'm going to assume. And so my CD is 2.2. So I get this is equal to 2.2 times 1/2 times 0.00238 slugs per foot cubed times 44 feet per second squared. And then my area here is again the frontal area. So whereas in the first part, this area I used up here was the area of the sign here. Now I'm looking for the area of the pole, which is right there. And so I'm going to multiply that by 3 inches times the height, which is 5 times 12 inches, and divide by 144 again to get it into feet squared. And when I do that, I get 6.34 pounds force. And so now I can plug those back into my moment equation, which says the bending moment equals 2.5 feet times force of drag of the pole, 6.34 pounds force, plus 5 plus 17 over 12 feet times the 22.7 pounds force, and we get 162 foot-pounds.